settled in here. So today it is our pleasure to welcome Sue Smrekar to give our colloquium. Sue, a little bit of information about her. You got your bachelor's from Brown, is that right?
Yep.
PhD from SMU. You've been at JPL since 1992, is that right?
That is correct.
A few other places.
I'm coming up on my
in between.
My 25-year pin.
Wow. A pin? 25 years.
Well, I don't know what it is, but yeah. It's coming up. It's coming up.
I don't even know.
For better or worse.
But yeah, so Sue has been a planetary geophysicist, geodynamicist, doing a lot of work on both Mars and Venus, as well as other objects. She has been the, the deputy project scientist on MRO, the deputy PI on InSight, and the PI of, fingers crossed, the VOX mission to Venus. She's been awarded numerous awards, including the NASA Exceptional Scientific Achievement Medal. You've been involved in VEXAG pretty heavily over the years. And today she's going to talk to us about Venus's well-kept secrets.
Thanks.
Okay, great. Well, I'm happy to be here this afternoon to talk about my favorite planet, Venus. This somewhat garish image, it shows Venus, Earth, and an imaginary exoplanet. And it's a recycled graphic from this conference, Tectonics and Geodynamics of Earth, Venus, and Exoplanets that we had a few summers ago at Caltech. And so I'm going to talk about some of the reasons why studying Venus may tell us things about Earth and exoplanets, but there are a lot of other ideas too about why Venus is so relevant to these other bodies. So, you know, if this is the topic you're interested in, I suggest you go check out those abstracts as well. So my collaborators, in particular Anne Devay at University of Paris Sud, she is doing, she's also a geodynamics geophysicist, and she's done these great tank models, which I'll show you some results from. But I think they have really a lot of ability to model processes in ways that numerical models can't do, and have been it's been very interesting for Venus. And then a couple other people, Steve Tomlinson was an undergraduate for a couple summers, and was on this paper with Anne Devay and I, and I'll show a little bit of data from Niels Mueller, who's a postdoc right now. Okay, so I'll talk about why we should care about Venus if we study exoplanets. And then I'll talk about some myths, which, if I'm using a more scientific word, I would say paradigms. And it was such a long time ago. Can you guys hear okay in the back? Okay. So it's such a long time ago that we had new data for Venus, for the surface of Venus, that some of these ideas that have been around for a long time really need to be reevaluated in light of things we're learning about the solar system, about Earth, and so forth. So really I want to go back and talk about some of the things that have made their way into textbooks, but perhaps need to be reconsidered. So in particular, I'll talk about what do we know about interior volatiles, what do we know about resurfacing and the sort of interplay between craters and other geologic processes. What does that mean for the surface of the planet and the dynamics of the planet? And in particular, I'll talk about subduction. And this was an idea that came out right after the Magellan mission in the early 90s. People, proposed that there was subduction happening on Venus. Then it was kind of there were arguments made against it, and I felt like most people, including me, said, "Oh no, it's not subduction." But I've changed my mind, and so hopefully I can convert you too. And in particular, I'll talk about the new case for plume-induced subduction. It's something that's been studied a bunch for the Earth, and we have examples of how it might work from these laboratory experiments. I'll show you why I think that these experiments are applicable to Venus. I'll show you some examples, and then try to extrapolate from there. What are the conditions that we need to have plume-induced subduction, and what might that mean for trying to predict should exoplanets have this kind of process? And of course, the reason that subduction is so important is that it's thought to be the stepping stone to evolving from a solid planet planetary lithosphere to plate tectonics. So that's why I feel like it's so important to try to study this process potentially happening on another planet today. Okay, so here's I'll get on the same page about some of the facts about Venus and why it, I and other people have given talks calling it the exoplanet next door. It's kind of this great cosmic accident. We have a planet that is so much like ours in our solar system. It's kind of the ideal control case. We think it started out initially very similar. How did it end up so different today? So it's often called Earth's twin, only 5% smaller, same bulk composition based on density as well as limited surface composition measurements. We know it once had a shallow ocean's worth of water. People have modeled it, modeled the evolution of Venus and the climate, and suggested it may have been habitable even before Earth was. We know it has very diverse geologic activity on the surface, and it's relatively young, about 1,000 craters on the surface. If you kind of extrapolate the number of craters on continents to the whole surface of the Earth, they're kind of comparable in terms of the number of impact craters. But there's the whole evil twin part, the runaway greenhouse atmosphere that gives it a surface temperature of 460 C, 90 bars of pressure. It's largely CO2 and has about 3 ppm of water. Now, that's a very low number, but actually the total amount of water in the atmosphere of Venus is not so different from the total amount of water on Earth. It's just Venus has a much denser atmosphere, and 90 bars is sort of equivalent to about 1 kilometer under the ocean. And of course, it has no magnetic field, which was a surprise for such a large planet that should have a similar amount of. We believe it does have a similar amount of radiogenic material based on measurements at the surface, and so it has a big heat engine, and so why no magnetic field? So for in terms of exoplanets, I like to say it's still the most Earth-like planet in terms of size, density, incoming radiation. Someday I'll say that and someone will jump up and correct me. We haven't done that yet today, but I'm sure an exoplanet scientist will do it someday, but as far as I understand, it's still true that it's the most Earth-like planet we know of. So the question is, how did it evolve so differently? So one of the big differences is the lack of plate tectonics, and before there was topography data, and this shows topography data for Earth and Venus at the same resolution. So before this topography data was available, people predicted that there would be plate tectonics on Venus. Like I said, similar radiogenic budget, similar size. We thought it would have a similar geodynamic evolution. But we even in this resolution, we can see evidence for spreading centers. If you know where to look, you can see evidence for subduction zones, both ocean and oceans under continents. You can't see transform faults at this resolution, so if there were transform faults on Venus, we very likely wouldn't see them. But we do see rifts. We see rifts through here, and you can't see them so well, but these two areas are also rifts. We think that there may be features that are analogous to continents on Earth. We don't really have all the geochemical information we'd like. There's some evidence that, oops, not that one, but this one is actually does have a low iron, perhaps felsic composition, but we don't have data for these other features to tell if they are in fact like continents on the Earth in terms of their composition. Then there's, as I said, there's this idea that there may be subduction. And in fact, this is one of the largest of those features here, and there's some other ones in here that have been proposed to be subduction, and I'll show you the arguments for that. There's also good evidence that there are active mantle plumes, both from their morphology and from the gravity data. So here's one, and here's one. Those are the largest ones, and there's a bunch of smaller ones as well. Okay, so why should we care about plate tectonics from an exoplanet perspective? Well, when you have a limited amount of information, the density, the size, if you're lucky, the incoming insolation, and you want to predict, is this really going to be an Earth-like habitable planet? You have to do a lot of modeling, and so a lot of the focus in terms of geodynamic modeling has been on assessing whether planets are likely to have plate tectonics. So, and that's believed to be an important factor for habitability on the Earth, in that it allows for recycling of volatiles via subduction, as well as release of volatiles from the interior. And so this is a nice cartoon that I grabbed off the web of subduction carrying volatiles back into the interior and being lost from the interior through volcanism and spreading ridges. And I'm going to talk about volatiles in a second, but if we believe that planets start out with all their interior volatiles, and that atmospheres are largely formed through the process of outgassing via volcanoes, then it really matters whether or not planets have plate tectonics, or if they don't have plate tectonics, what their geologic evolution has been, because that process of volcanism and geologic activity is a process by which hydrospheres and atmospheres are largely formed. So you can also get creation of different environments by having variable topography from plate tectonics. It likely plays a role in creating the dynamo through significant heat loss from the core. And people are talking about water-rock interactions as a potentially important process for creating life. We do know that only Earth has full-scale plate tectonics, and this is the only place where we found life. Who knows? Does it have any link? Maybe, maybe not. So this question has been out there for a long time. Why doesn't Venus have plate tectonics? And I and bunches of other people have written about the possibility that it's too dry to have plate tectonics. And really, when you talk about plate tectonics from a modeling standpoint, what that means is that the interior convective stresses are strong enough to break the lithosphere. So, so it matters how strong the lithosphere is and how strong the convective vigor is. So the idea that it doesn't have plate tectonics came about largely because we thought most of the water came from comets, and if the surface of Venus was very hot, there's no recycling of volatiles back into the interior. The idea was that, well, perhaps Venus is dry in the interior. There's some evidence that there's no low viscosity zone in Venus, and a low viscosity zone underneath the oceanic plates is thought to help move the plate, make it easier for the plates to slide around. It was thought that a low viscosity zone is due to water in the Earth, although there are now new ideas for why there's a low viscosity zone underneath the oceanic plates. The idea was also that if there's no water in the interior of Venus, the lithosphere would be too dry and thus too strong to actually break and allow plate tectonics. And then another idea is that you actually need clays in these faults to help sliding, which again would be a problem if there's no interior water. But there are some new ideas about why Venus lacks plate tectonics, and one is that it's actually too hot. When you start with a solid outer shell and start creating faults that break the lithosphere, you need to have a whole system of these faults that go through the lithosphere in order to allow plate tectonics to actually form plates and set up an entire system. But if you basically break the lithosphere in one place, and it's so hot that minerals can grow across those faults, effectively removing those weak zones, then perhaps that prevents the development of plate tectonics. So I'll come back to that idea in a bit. Okay, so so I've been talking about this idea that Venus is dry, and I think that this needs to be reevaluated in light of a lot of the information we have about volatiles through the solar system. For one thing, every time we go to a new body, we see more and more evidence of volatiles, from ice on Mercury to a young surface and volatiles on Pluto. We also know that there's more water in the interior of the Earth than had been thought previously. So it seems that planets are very likely to start out wet, and especially what we've been learning about volatiles in comets and in various asteroids, it seems that at least the preliminary results from Rosetta suggest that cometary water may be a fraction of the water on the Earth, but not a significant fraction. So again, it comes back to this idea that planets start out with the bulk of the volatiles that they have, and that as geologic processes release them, they are added to the atmosphere. And we have also learned some things about the distribution of volatiles from studying exoplanets. We've seen very large, low-density exoplanets very close to their suns. So, it seems that, this idea that there's a simple gradient in the volatile content away from the sun doesn't work in all solar systems. And there's also been attempts to try to explain this of, planets forming and moving around after they form. So, just distance, pure distance from the sun is not an indicator of planetary volatiles. Okay, so, and I should say, please interrupt at any time if you want to jump in on any of these topics. Especially volatiles is not really my topic, but this is what I get from various sources. So if you disagree with me, jump in. Okay, so what do we know? Okay, so I talked about this no low viscosity zone in the upper mantle on Venus, and that's based on gravity and topography, specifically geoid topography ratios and hotspots. And from modeling how plumes interact with the lithosphere, it was shown that on Earth, these hotspots appear to have a low viscosity zone, as well as from other data, seismic data and so forth. But there's, from the gravity, there seems to be no low viscosity zone on Venus, and that has been used in the past, at least, to infer that the interior is dry. It could be that a low viscosity zone is due to melt or other processes besides simply water. And there's very high topography, up to about over 10 kilometers on Venus. There's also 1 or 2 large impacts, and that topography hasn't gone away. So that's been used to infer that the crust, the lithosphere, is very strong and thus dry. The alternative is that these could in fact be relatively young features, and they have to be pretty young or actively supported in terms of the high topography. Some information that suggests that Venus is still wet. There's argon isotope data that's been around for a long time. People have suggested that there's a fair amount of uncertainty both in the data and our understanding of how argon is degassed from the interior of the Earth, how much is in the interior of the Earth, how much is in the interior of Venus. But all of those things aside, it does appear that Venus is less degassed than Earth, roughly 25% versus roughly 50% for the Earth. And there's been data from the recent orbiters studying the atmosphere that suggests that there is active or recent volcanism. Modeling the amount of water and sulfur in the atmosphere suggests that it needs to be resupplied on the order of tens of millions of years time frames, and there's been some work looking at the oxygen that's lost through space, and it seems to be being lost at a similar rate as Earth. Now that's a pretty new result and maybe controversial, but it's an interesting result. And then there's various evidence for active and recent volcanism, as well as increasing atmospheric sulfur over the last 10 years, which one interpretation at least is active volcanism. So these are at least sulfur coming out. There's not clear evidence at this point that water is being degassed, although it's quite hard to degas water given the very high pressure. Okay, so the next thing I want to talk about is catastrophic resurfacing. And this result that there were about 1,000 craters on the surface of Venus, and that very few of these craters were modified, was very surprising when it was initially discovered. Here's a clearly volcanically flooded crater, but most of them are quite pristine. There's no clear evidence that they've been modified. And the other thing is that these craters, their distribution cannot be distinguished from a random distribution. So these two factors of there being this global, apparently random distribution and very little modification led to this idea that Venus catastrophically resurfaced. And this is a really cool idea. People could assume that if you had to volcanically flood the entire surface of the planet, of course that would produce massive volatiles and climate change. It also inspired models to look at episodic plate tectonics as a way to resurface the entire planet and to get the heat out of the planet. But that's not the only model that fits the data. This shows some various types of resurfacing models. So you have interplay between blue impact craters, red resurfacing patches, which could be volcanism or some other geologic process that tectonically removes craters. And you can have these occurring on different time scales. So this is the catastrophic model. Everything is completely reset, and then impact craters are laid down, which gives few modified craters. Then there's an equilibrium between impact craters and resurfacing processes that they proceed along at a steady rate. And then there's regional resurfacing, where you have resurfacing occurring in one place, and then previously it occurred here, and then before that it occurred over here. So resurfacing is variable in space. And a lot of people have investigated this approach, and essentially you can get different models to fit. There's only 1,000 craters, so that's probably not super surprising. But one thing that's interesting is that for those models of equilibrium resurfacing, you get a good fit to the data if you have a patch size with a radius of from hundreds to 1,000 kilometers. So store that away. We'll come back to that. So you can also take a different approach to try and understand the history of the craters. One thing that's uncertain is whether or not how many of them have actually been modified. 80% of the craters have radar dark, smooth floors. That could be a result of volcanism subsequent to crater formation. And this paper takes a look at that idea and provides evidence to suggest that there is volcanic flooding using stereotopography data that's available for a small fraction, about 20% of the planet. And if this study is correct, and in fact actually 80% of the craters have been modified, you can predict an age as young as 150 million years on average. And a completely different approach to this idea is from Botke, who suggests that the near-Earth objects are in fact the source of all the impact craters on the surface of Venus. Again, this is kind of a controversial idea because it contradicts scaling laws from modeling how big an impactor should be relative to the size of a crater. But if this is correct, you would also get quite a young age. Another approach to trying to understand the history tries to look at the parabolas and halos and their removal as a function of time. On Venus, you have every impact crater bigger than about 10 kilometers is thought to produce these very large, fine-grained deposits of material that are blown downwind. You can actually see them in this map of topography and radar brightness. And so you can see these very dark areas that are prominent in the data, and that's this very fine-grained deposit that makes a smooth radar return. Appears dark in radar, and clearly these features are removed over time. And so about 10% of them still have these parabolas. And so there's been a lot of work trying to also include the removal of these features to try to estimate the age of the surface. And from this kind of work, you can see that there are actually areas of relatively different age on the surface, that it's not all one uniform age. Okay, so getting on to, did I start my timer? Okay. So getting on to subduction. Again, very soon after this data was acquired, there were a number of papers that came out saying we have evidence for subduction on Venus. And you can see this is a terrestrial subduction zone, and this feature, ARTEMIS corona, at the same horizontal and vertical scales, morphologically similar, and these are the sort of criteria that they use to try to identify subduction zones. Narrow, deep trenches along a gate, along strike, or arcuate in plan form. They have topographically a ridge, trench, outer rise profile. They have large curvatures implying a certain strength of the lithosphere, and they have fracturing parallel to the strike, and no fractures that cross the trench. So there are a lot of places that actually, and I'll show you these profiles in a second to look at the mechanical strength. So those are those profiles across the trenches, and you can model this as elastic flexure, and you get an elastic thickness on the order of 30 kilometers for both of those trenches that I was just showing you. So they seem to be deforming in the same way. So I'm just gonna take a little aside here from subduction and talk about what is a corona, because most of these sites on Venus are areas that are called corona, and so these are there are about 500 of these features on the surface of Venus. They have both tectonic deformation and volcanism. They have this crazy array of topographic profiles. Their mean diameter is about 250 kilometers, and the one that I was just showing you, Artemis, is this major outlier at 2,600 kilometers. Nothing else is half as big as that. There's been a huge number of formation models for how you get this array of topography. And most of the models focus on mantle upwelling, starting out with domes and plateaus, and then evolving to some of these other features over time. You can see there are radial fractures in some of these features, which also tends to support the fact that upwelling would be involved in these. But a number of these other models also give you at least some of these topographic forms. So now you have at least a first order idea of what a corona is, in which I'll be showing you a few of these. Okay, so there were these arguments put forward that these features morphologically and from a standpoint of deformation appear to be like subduction zones, but then there were also arguments against that, and this is one of these features about 500 kilometers in diameter, and people said, okay, well, they actually have all these radial fractures across them, and so if it's an upwelling, which is consistent with the presence of these radial fractures forming first, it doesn't make sense that they are subduction zones. And so the next few slides come from this paper saying no subduction, no spreading on Venus. Okay, so one of these arguments, in addition to having these radial fractures in the interior, some of them have fractures that go. This feature here and here were proposed to be subduction zones. There was some evidence that some of the fractures go across these subduction zones, so that was used to argue against it. However, that doesn't happen on very many locations on Venus, and there are actually a few rare locations like that on Earth where you can see fractures that cut across subduction zones. And then in places where there are multiple corona along rift zones, the inferred direction of the subduction changed along the strike of these chains of corona and rift zones. So that was used to say, well, on Earth you have subduction going in one direction, you don't have it flip-flopping back and forth. However, that's not a big problem if the subduction is initiated by each of these individual corona. So, some of the authors of this original idea tried to address this sort of dual nature of the features as having both an upwelling origin and the morphology of subduction. And this is for a Venusian and a terrestrial example. And so their idea was that, okay, well, at rift zones, the lithosphere is weak, it's broken. That allows a place where subduction can be initiated when you have loading of the lithosphere by volcanism above a plume head. So this was one idea to try to incorporate both those aspects. This is another idea. This is Artemis corona. Here's the trench. And they're suggestion was that you get a plume that would break the lithosphere and allow foundering of the sides of the plates, and as the mantle flows in, you would get small-scale convection to form these smaller kind of circular features in the interior. And I have to say that I was never super convinced by these cartoons. It just didn't really make sense to me. But I just wanted to point out that there were some models that included not subduction but delamination as a way to get some of these outer rises. And this was a now 20-year-old convection model that where a plume came up and allowed initiated dripping off the bottom of the lithosphere, and this dripping followed by isostatic rebound of the crust formed some of these bizarre topographies. But there's a really big important difference between delamination and subduction. With delamination, you don't get resurfacing. You don't get the surface removed by having a drip off the bottom. You don't recycle the crustal material, and you don't fracture the whole lithosphere. So delamination isn't a step towards getting plate tectonics. Okay, so fast forward, people are really, a topic in terrestrial studies is the initiation of subduction right now. And so there are a bunch of different ideas about how subduction and thus plate tectonics actually started on the Earth. And this is one of these numerical models where people have proposed subduction, plume-induced subduction for the Earth. And you'll see that it looks very viscous, this behavior. And an issue for this model and for simply breaking the lithosphere to start plate tectonics, no matter what kind of model you have, is the strength of the lithosphere. The strength that you infer from laboratory measurements is really large compared to the stress that you create in a numerical model of breaking the lithosphere. So pretty much all of these models that predict plate tectonics, that predict this kind of breaking and extreme deformation of the lithosphere, have to use some some pretty low viscosities for what's going on underneath the surface. And you can kind of just see that this looks like a kind of a low viscosity result. So maybe this works, but it's kind of a stretch of based on what we understand about rheology. And there's probably problems with laboratory results showing how strong rock is. We can't deform things on the time scale of actual tectonic events. And so pretty much you have to infer some other kind of weakening of the rock to get these kinds of things to happen. And one of the ideas is that heating above plumes helps with that problem. And this is another attempt to form subduction and break the lithosphere on the Earth. And then this is an example where people have applied this approach to Venus, and pretty much you get it seemed to the crustes seem to be very viscous, and you get actually convection within the crust to form all these kind of crazy topographic events. And so I've always been a little bit skeptical about these because you require such a weak low viscosity material in order to deform that rapidly. So I started this collaboration with Anne Devay, who's been working to model plate tectonics in a tank-like setting for a long time, and has really finally found the right combination of materials that allow you to do all the required scaling in terms of the interior convection, the strength of the lithosphere, that really fine materials that behave like planetary lithospheres and mantles. And it consists of a polymer and a colloidal solution. As the surface dries from above, these colloid material become more densely packed as liquid is removed, and that creates a lid that behaves progressively, it behaves elastically at the top, viscously at the bottom, and so there's this kind of a schematic. There's a fan that helps create drying in the tank, and it's set up to try to record the surface deformation. One of the things that's really helpful about this is that you have processes going on at all different scales. You have from down to the scale of the particles up to the scale of about a meter for convection and buoyancy. And one of the things that occurred as this top layer is drying is that you get microfractures occurring in the elastic layer. And at first, Anne was disappointed to see that, but later realized that in fact, lithospheres do have fractures, and so it's been actually beneficial in terms of getting things to form asymmetrically. Okay, so, and the other great thing about this is that you get these deformation structures occurring in 3D. If we go back to some of these models, basically what this model predicts is a viscous sheet of material going down, in a circle. And you can imagine that geometrically that's eventually going to be a problem. But in the laboratory, you can actually see the deformation occurring in 3D. And so this is a cross-section across the tank. You have a hot plume coming up here. You have a plume that's formed, a slab that's formed as lithosphere is broken above this plume, and this has started to founder down into the convecting area. On the surface, you have these fractures forming, and you get basically a partial arc of fracturing, because as this thing is trying to push down in, it can't just drip down in a viscous sheet. It actually fractures and rips. And this shows a little bit better. I forgot to bring my demo. Oh, here we go. Yeah. So this shows the surface of this tank, and here are these features that form on the edges of the plateaus, kind of these ridges and trenches. And this is sort of an illustration of what's happening. You get ripping that forms as the elastic part is foundering down below, and then the white part is new material. And this shows the progression of the slab as it's falling in. You can see it hasn't occurred right in the center of the plume head. It's occurred off to one side. So you have ripping and foundering on this side, and then a different kind of scale over here. I find it's if you do this at home, it helps to think about what's going on. If you take a pen and you stick it in a piece of paper, you have you have deformation. It's going to have little bits that have ripped. You don't have this like viscous drip of material that's going down. So you actually just get partial slabs that form around the deformation. So this kind of shows in cartoon form what's happening. You get the plume uplift and extension, and then you get actually material flowing up. In reality, it would be like volcanism occurring at the surface, and that loading by volcanism actually starts the lithosphere bending down. And this is kind of crazy to look at. Basically, Anne tried to take a piece of the stiff skin lithosphere in the top and look at it under a microscope. And there's these kind of crazy bubbles going on, so ignore those. But you see deformation at the edge of this trench, and you see also these extensional fractures, and that occurs where the trench is curved, basically as it tries to accommodate moving down in an arc. You get extension perpendicular to the trench. Okay, so these laboratory experiments resolve some of the things that in a way they're very analogous to the ideas that were put forward by Sandwell and Schubert, sort of more in cartoon form, but it also goes beyond that and shows really in 3D what the deformation at the surface should look like. So it's consistent with both kinds of deformation that produces these partial arcs of subduction, not like a big viscous ring of subduction. And we see these small strain extension perpendicular to the areas of high curvature where the plate is stretching as it's pushing down around an arc. It's consistent with having sort of rollback, basically just foundering of the lithosphere. at different, going in different directions along, say, a rift where there's multiple corona. Okay, so here's again this giant corona, Artemis, and here's the trench, and you can see it's like a partial trench. It's not a full circular trench as you would predict in a numerical model. This is just a profile across the bending lithosphere, and an illustration of these fractures, these extensional fractures that occur perpendicular to areas where you have a strong curve in the arc. And yeah, so this is radar data. And topography is shown here. The trenches are a couple kilometers deep. Artemis is kind of unusual, not only because it's the only one that big, but it also has these areas that look like rifting through the center. And okay, so we tried in this paper that came out this year, we tried to look at the gravity data. The gravity data on Venus is not great, and it's especially not great in these two areas. So, you know, we tried to do what we could with the data, but the resolution here is about 400 kilometers. And this is the Bouguer gravity data. So effects of the topography have been removed. And you can see that there's definitely anomalies in association with these areas that appear to be rifting. And there's also an anomaly associated with a larger part of this trench. And I'll point out that this is not what you would expect. This is a Bouguer low, consistent with having low density material at depth, not high density. And so the only scenario that makes sense in this context is having this being a relatively old feature in which the subduction has happened and the slab is essentially thermally equilibrated, and what you're seeing now is the primarily from crustal material at depth. And we tried to look at the since the resolution is basically too low to do anything in terms of admittance, we looked at GEOID topography ratios, and so black is for this whole area, red is for these points, and then other areas that had distinct gravity anomalies. And you can see that the area near the trench definitely has the steepest slope in terms of plotting GEOID versus topography. Steeper slope implies a greater depth of compensation, so it seems to be consistent with material at depth. We also tried just having modeling a slab at depth based on what was inferred from the lab experiments. Basically, a slab that would be less than the diameter of the corona, as well as a fairly steep dip, and you can in fact fit this with a relatively thin plate and primarily with crustal material. We looked at a second feature. This is the second largest corona on Venus. Here's the trench, and again there are these fractures that are going out away from where the trench is curved. It also has this topographic profile, which is consistent with flexure of the lithosphere. And this feature is interesting in that it has these huge volcanic flows, and these flows are consistent in terms of their volume with something equivalent to the Deccan Trough. So a huge amount of volcanism is pouring out, has poured out in this particular area. And again, so we did the same kind of gravity analysis. This is a smaller feature, so it's we don't see a lot of differentiation of these different areas, and pretty much you see the signature of what is consistent with a plume at depth in the center, and this area here, which is near where the subduction zone, inferred subduction zone is somewhat steeper, but it's not as distinct as in the larger area where these features separate out a bit more. And again, we tried just putting in a slab model to see what would happen, and here it's consistent with a strong dip and a relatively thin lithosphere, 100 to 150 kilometer thick lithosphere, here getting a cold slab seems correct. This is an area, I don't really have time to go into this whole argument about recent volcanism, but this is an area where there's been inferred to be recent volcanism associated with these giant flows, as well as some of these other flows in the area. And so, based on these ideas of how do you interpret surface emissivity data, this area is an area where there's high emissivity and inferred to be recent volcanism. Okay, so that's I think so that's the evidence for the possibility of rollback subduction forming on Venus, basically, having lithosphere break and founder. But could that lead to plate tectonics? And in order for that to happen, really what you want to have is the subduction to move beyond just the plume. And there are places where this is another relatively smaller corona. There are places where the edges of the corona appear more linear. So you can interpret that as the subduction having migrated beyond just the initial lithospheric disturbance above the plume. There are also these areas along rift zones where there's morphology of trenches that may have formed where the lithosphere is broken by extension. So there's some possibility that these can form beyond just the plume head. And this is an interesting example. Here's a corona that's most of it is intact, but it's also continuous with this trench that wraps around one side of this very large plateau. So you can imagine, I don't have a model that shows this, but you can imagine that if you did get subduction occurring, foundering a part of the lithosphere above this corona, and if it continued to peel back, especially this is a through-going rift zone, so the lithosphere is very weak, so if the lithosphere started to peel back along this rift zone, it could have actually migrated out and formed this trench. Another interesting thing we're still working on, but this is the 1 micron emissivity data in this area, and you can see there's some large, very viscous lava flows in this area, and they occur in areas where you have low emissivity, which could be a different composition, perhaps associated with having, perhaps more volatiles, more carbon dioxide or something that occurred that was introduced into the melt and helped form such low viscosity flows. So, if we do have subduction, what are the conditions that allow this to form on Venus today? So trying to use some analytic models to extrapolate the conditions that are needed. One thing that you need is for the lithosphere to be initially gravitationally unstable. It has to be dense enough to want to sink into the mantle. You have to get the entire lithosphere to break. And as I was talking about, it's hard to do this in numerical models. People generally call on shear heating or damage zones or cracking of some kind, like in the oceanic lithosphere, contraction cracks as the lithosphere cools. So it's generally hard to get the entire lithosphere to break, but it occurs more easily in extensional regions. Rock is weaker under extension than compression, so these are generally the kinds of scenarios that people look to try to break the lithosphere. And then once you break it, you have to load it, and it has to be essentially weak enough to break, but strong enough that when you do load it, it'll actually have the strength to bend and not just break off and get recycled immediately, kind of lava lake style. Okay, so we looked at the strength of a plume that's needed to cause extension of the lithosphere. You have to start out having a large Rayleigh number in the mantle to allow hot plumes to form. and then you have to have a buoyant enough plume to break the lithosphere, and there's some various models for what that might look like. This particular equation is from Koch and Magna, which probably, given the boundary conditions, probably an overestimate of the amount of buoyancy that you need as compared to other models. We also have this issue of how strong really is a lithosphere, how much stress you need to break it. And this is a relatively recent paper that suggests that maybe the work done in the laboratory is overestimating the strength. But you can anyway, in any case, you can estimate the radius of the plume and the density difference, and get an estimate of the plume size needed to break a given lithosphere. And then, okay, so what about bending the lithosphere? This is taken from a paper by Kemp and Stevenson, trying to look at this problem of initiation of subduction. And they looked at continental lithosphere versus oceanic, and extension into the suture zone, and mantle material coming up and actually flowing out onto the surface. You know, I think on Venus it's probably more likely a bunch of pressure release volcanism, sort of as we saw in that Quetzalcoatl Corona example. And then you can look at, okay, how much loading do you need in order to actually get your lithosphere to start to bend? So they came up with this equation where if this is greater than 1, you can get subduction to occur. Your lithosphere will be strong enough and it will start to bend. And so these are the parameters: the plume lithosphere density contrast, the thickness and strength of the lithosphere, the viscosity of the hot plume, the depth at which, the temperature at which a plate will behave elastically. And so for contrast between Venus and Earth, the main ones are in terms of surface temperature and perhaps the thickness of the lithosphere. And possibly plumes, although we infer that plumes, because they seem to be similar in size, we infer they have a similar buoyancy on Earth and Venus. Okay, so this plots lithospheric thickness versus mantle potential temperature using that equation I just showed you. So given the higher surface temperature in Venus, Venus plots here. So for this is thermal, not elastic lithosphere, but thermal lithospheric thickness. So in this case, for Venus, you don't get subduction for presumably a mantle temperature of about 1300 today. And on Earth, it plots down here because of the lower surface temperature. And presumably in some areas, the lithosphere is going to be too strong to actually break it in the first place. So here's the temperature today, but here's the temperature of the mantle, presumably under the Archean Earth. So for Venus today, it may be possibly the lithosphere is too weak locally for this to occur, and it may only occur for larger plumes that are large enough to actually break the lithosphere, unless you have something else going on, such as rifting that already broke the lithosphere. So for Earth, from this kind of simple analytical attempt to extrapolate, it's hard to get subduction to occur today. However, in the Archean Earth, with higher mantle temperatures, it may have been much more easy to get subduction to initiate with this kind of mechanism. Okay, so what if we gather from there being subduction on Venus? So it seems like some of these large corona may be sites of subduction. They seem to be active today based on the gravity data, the emissivity data, at least some of them. It's possible that in some cases that propagates actually beyond just the foundering of the lithosphere, so-called rollback subduction. It may actually start to rip the lithosphere beyond the plume head. It can actually cause local resurfacing. If you have that new material coming to the surface where the plate has foundered, you could actually recycle the crust and get resurfacing on the scale that's consistent with these models of equilibrium resurfacing. It may return volatiles into the interior. We don't really know what the volatile content is of the crust and lithosphere. On Earth, we believe that subduction is important in creating the felsic crust, and we do have potentially analogs for felsic crust on the Earth in terms of these tesseract plateaus. And in fact, one of the inferred subduction zones occurs in association with the largest terrestrial plateau, Ishtar Terra. And then, so maybe we have subduction. Why not go plate tectonics? And again, it may be that it comes back to this idea that the lithosphere is too hot, that you can't have these through-going lithospheric fractures hanging around long enough to form into a network, and that's work by Bercovici. So, we may have a good analog for early Earth on Venus, and it could be that subduction was simply easier to get going with thinner lithosphere and with other mechanisms as well as this. It makes sense in terms of this framework that as the lithosphere thickened, you could eventually lead to plate tectonics as the lithosphere cooled. Maybe initially you had maybe the lithosphere was too hot to anneal, but as the lithosphere got cooler, it could preserve those fractures for longer time periods, allowing plates to organize. So, and just coming back to these laboratory experiments, different conditions have produced stagnant, sluggish, and plate tectonic regimes, and these progress from sluggish to plate tectonic to stagnant as the lithosphere gets stronger. And so the regime that looks like what we see on the surface of Venus today is this sluggish regime, where you can get the subduction starting, but it doesn't organize into full-scale plate tectonics. We have some more work to do to think about really how to extrapolate this mechanism to conditions in general, more work to do to try to really estimate the properties of the lithosphere in the area where we see these processes, but we are looking forward to trying to do that and see what we can learn from Venus about exoplanets and Earth. So thank you.
Questions?
In your gravity analysis plots, you mentioned the geotopography ratios and the slopes of the line. It looked like some of the lines had intercepts that were not at 0, 0 if you were to extend them out. Can you comment on what, if any, implications that has for geodynamics?
Yeah. I mean, well, it could be regional variations in the topography and gravity. For example, Artemis Corona is right up against the some other large topographic features, so there's kind of a regional slope. So I can't say that I've thought about that question in particular. So I'll have to think about it more, but it may be that there's regional effects that could affect that. I don't know. I'll think about it.
What sort of data sets do you think you would need to look for that annealing process, if that is the sort of explanation?
You would certainly want very high resolution topography to be able to look for, like I said, even if we had transform faults on Venus, you really couldn't see them with the data that we have now. And I think from high resolution topography, you could see much more clearly whether or not there is, how these different processes interact. For example, in that Quetzalcoatl corona, I guess I'm being recorded, so I shouldn't say this, but there is actually some possibility that there is an extensional zone near that feature. So it's possible that. So here's the area where this plate occurred, or this area is seems to be fracturing in response to possible subduction of this trench, and there's possible extensional zone here. So can you actually see annealing? No, it's hard to tell what's going on even in fault zones on the Earth, right? But if we had high resolution topography, we could look for a better understanding of how the actual faulting is occurring. Like if this is subduction, you should probably see some transform faults associated with it. So we can start to look for more of the faulting that you would expect from all of these processes, and there may be more faulting going on than we actually can see at present. So if we get high resolution topography and see that really all these things are totally isolated, and from that we'd also be able to get better estimates of the elastic thickness, so we can have a better sense of how hot is this lithosphere. We could move towards that question, but of course without really being on the surface and sampling at depth, and it's hard to get at exactly that question, but we could understand better the ability of the lithosphere to break and see the manifestation of that.
In order to get the plate to bend, one model you showed had mantle material erupted onto the surface. Has that ever happened on Earth?
Yeah, so so that was this model that was proposed for the Earth, and no, I don't think that's particularly likely. But I think with a mantle plume, so that was just that was for a passive margin kind of explanation for how, and that was something that's been tossed out a lot for the Earth, passive margins foundering to produce initiation of subduction. So there's no buoyant material. It's just mantle that when the lithosphere is stretched apart, it flows up onto the surface. So no, I don't.
But
I would agree that that's not very likely.
It's not what we get, though. We get partial melting and basaltic
Right.
lava that flows up.
Right. So I think in reality is that you can get massive partial melting. Like I said, this volcanic complex is something on the order of the size of decant traps. So you can, under some plume-related circumstances, get massive quantities of stuff on loading the surface. Yeah, and that was just an analytic solution that made for a nice analogy, right? yeah, definitely don't take it too literally.
One question is it possible we're catching Venus at the beginning of its next big plate tectonic cycle? Is there an observational test that would tell us that, or whether equilibrium resurfacing is really the answer?
Yeah, so I think that new data could answer the resurfacing question. Basically, I think that what we would want to know to understand what the rates of resurfacing, or what type of resurfacing has been going on, catastrophic versus equilibrium, is really what's going on at the impact craters. Is that dark material volcanic? Is in the stereo data they've provided evidence that the dark floored craters are shallow on the interior and shallower on the exterior. That there's basically flooding in around the ejecta blanket. But it's kind of on the hairy edge of what you can tell in this stereo data, and that's only for a limited number of craters. So to be able to globally find out, are those dark floored craters actually flooded, and also find out what is removing the parabolas. Is it aeolian processes? Are they being covered with volcanic flows? So I think that would help us understand, has there been catastrophic resurfacing occurring in the past or not?
All right. Well, thanks, Sue, again.